This is section 3.4, zeros of polynomials, and we're going to jump right in and apply the rational zero theorem. So basically, the rational zero theorem gives us all of the possible rational zeros. That doesn't mean that they are actual zeros of a polynomial, but it gives us the possible zeros, and these will be rational. So what do? We are going to be writing P over Q in its lowest terms, and we're going to say that P, or we are going to use P as a factor of the constant term, and we're going to have Q as a factor of the leading coefficient, and each of these are denoted A sub 0, A sub n. So we have A sub n, which is that leading coefficient, and A sub 0 is that constant. So we will make that ratio, and we will list all of the possible rational zeros. This is not a difficult topic, but you do need to know what you are doing. So obviously, we have A sub n equals 4, and we have A sub 0 equals negative 15, okay? This is our constant term, and this is our leading coefficient, okay? So if we have our factors, and remember, P comes from the constant, so we have the factors of negative 15, and we're going to divide that by the factors of 4. And that's equal to, let's start with negative 15. We have plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. All of those are factors of negative 15. Okay? Now, let's talk about factors of 4. And those are going to be plus or minus 1, plus or minus 2, and plus or minus 4. So now what we're going to do is we are going to give all of those combinations. So what I like to do is start with plus or minus 1 and put that over 1, 1/2, and 4. Then I'll go to 3 over 1, over 2, and over 4, and so forth. Okay? So let's go ahead and list them. I'm going to start with plus or minus 1. So we're going to have plus or minus 1. 1 over 1 is 1. Plus or minus 1/2, plus or minus 1/4. Okay, I finished the 1. Now let's go to 3. Plus or minus 3 over 1, which is 3. Plus or minus 3/2, and plus or minus 3/4. Now let's go to 5. Plus or minus 5, plus or minus 5/2, plus or minus 5/4. And now let's go to 15. So we have plus or minus 15, plus or minus 15/2, and I've got one more. I'd like to put it in the same line here. And then we have plus or minus 15/4. Okay. So that's it. Those are all of the possible rational zeros. And as you can see, we have 2, 4, 6, 8, 10, and 12 of those. So there are a lot. Okay. Now, with this, we're going to find the zeros and the multiplicities. Now, this can be a little tricky, but what we want to do is begin with our P over Q's, okay? So, of course, we have a leading coefficient of 2, and then we have our constant term 3. So let's go ahead and have our factors of 3, and these are going to be our possible rational zeros. And then we'll have plus or minus 1, plus or minus 3, and then we have plus or minus 1 and plus or minus 2. So this isn't that bad. So our P over Q's, our possible zeros, are going to be plus or minus 1, plus or minus a half, plus or minus 3, plus or minus 3 halves. Now, what I like to do is I like to go ahead and just start with one that if I graphed this quartic, this is a quartic, and 1 0 jumped out at me, I might begin with that one, okay? So what I like to do is I like to go ahead and just put this in the calculator. And I like to just take a look at it. Okay, so we're going to zoom 6. And what do you see? Look at that. Do you see that at x equal to 1, it looks like we might have a 0 of multiplicity 2. So let's just take a look. From the graph, we might have a 0 of 1 with multiplicity 2, okay? And then it kind of looks like the other zeros are not on a crosshair. So we need to go ahead and see if these truly are zeros. Okay, so I'm going to close that calculator. Use the calculator to help you find a place to start. Okay, so we are going to put 1 in the box, and with synthetic division, we have 2, 1, -5, -1, and 3. And we're going to go ahead and drop that 2. And sure enough, 1 is a 0. Now we are going to work on a back-to-back synthetic division, but let's see what we have so far. What we have so far is that 2x cubed right here minus plus 3x squared minus 2x minus 3 is a factor. So let's go ahead and put 1 in the box again and go into that cubic. So we'll drop that 2. And you can see we were correct. And I can always just write remainder here, or an R. Zero is the remainder, okay? So what do we have right now? What we have right now are our factors. And we have x minus 1 multiplied by x minus 1 multiplied by, what is that? A 2x squared plus 5x plus 3. So now we have a quadratic. And if you factor that quadratic, so we have a 6 as a times c and a 5, so we'll add up a 3 and a 2, and we'll divide by 2x. And we will have 2x plus 3 multiplied by x plus 1. So the question here was to find the zeros and their multiplicities. So what would our zeros be here? Our zeros here are 1, and it has multiplicity 2. We have a 0 here of a negative 3/2, and then we have a 0 here of negative 1. So those are our zeros. Okay, now we're asked to find the zeros and their multiplicities of this cubic. So let's go ahead and find our P over Q's. We will have the factors of negative 5 divided by the factors of 1. So that will be plus or minus 1 plus or minus 5 divided by plus or minus 1. So really, we have a 1, a 5, and the opposite of them as well. So taking a look in the calculator, let's put that cubic in, and let's see if we can see a 0, a starting place for this 0. Can't really get that. There we go. So we have x cubed minus 2x squared minus 14x minus 5. And let's take a look at this, zoom 6. And as you can see, the only real 0 I see is at 5. The other ones look like they're not right on a crosshair. So let's go ahead and begin with 5. So we'll put 5 in the box, and we have 1, negative 2, negative 14, and negative 5. And our remainder is 0. So what does this represent right here? What we have is x squared plus 3x plus 1. So we already know that x equal to 5 is a 0. So we already have x equal to 5 as a 0. So we do need to find the other two zeros. So we're left with x squared plus 3x plus 1 equals 0. And we can't factor that. So we will use the quadratic formula, the opposite of b plus or minus b squared minus 4 times a times c all over 2a, and that comes out to negative 3 plus or minus root 5 over 2. And those are our other two zeros. So our zeros are 5 and negative 3 plus root 5 over 2. to raise that up a little bit. Okay, so now let's apply the fundamental theorem of algebra. You might see that as the FTOA. And basically the fundamental theorem of algebra says that if we have a polynomial of degree greater than or equal to 1 with complex coefficients, then we must have at least one complex zero. The linear factorization tells us that these constants here are our complex numbers. The conjugate zeros theorem is super important. So that if A plus BI, goodness gracious, if A plus BI is a zero of f of x, then its complex conjugate, A minus BI, is also a zero of f of x. Really important. And finally, the number of zeros of a polynomial is exactly equal to n complex zeros. And we do have to count the multiplicity. So let's give this a try. We're given that 1 minus 5i is a 0. So if 1 minus 5i is a 0, we already know that 1 plus 5i is a 0. So we will use synthetic division with both of these known zeros. And they do want us to find the remaining zeros, and then they want us to factor as a product of linear factors. So let's go ahead and put 1 minus 5i in the box. And I will tell you, you might want to spread these out, these coefficients out a little bit, because sometimes the complex numbers are a little bit longer. So we'll drop the 1. And you can use your calculator to multiply these complex numbers out. Obviously, we learned this in a previous class, but we could still, do that here. So if we're going to multiply 1 minus 5i and multiply that by negative 2 minus 5i, and let me make sure I typed that in correctly, we can see that that's negative 27 plus 5i, okay? And you can check the rest. I'll give them to you, but you can always check the rest. And then 1 plus 5i multiplied by 1 minus 5i is 26. And of course, we get that 0 remainder. Now, let's go into this with the other 0, 1 plus 5i. And we'll drop that 1. And that looks like we'll have a negative 1, sorry. And come up with that remainder of 0. So what does this represent? That represents x minus 1. So here are our factors. Let's write our zeros first. We have 1 minus 5i, 1 plus 5i, and what would that 0 be? It would be a 1 because that factor x minus 1, of course, would give us the 0 of 1. So now our factored form is x minus 1 minus 5i, x minus 1 plus 5i, and x minus 1. So if we multiply that out, we'll get x minus 1 plus 5i, x minus 1 minus 5i multiplied by x minus 1. So this is our factored polynomial. Okay, let's take a look at number 5. In number 5, we're told that x equal to negative 1/2 is one solution to this quartic, okay? So we are going to need some p over q's, some other possible zeros. So we will use 2 and negative 9. And so what we get if we look at the, well, let's go ahead and begin. But if you do look at the graph, you can see that x equal to 1 may be a 0. So that will be a good starting place. But let's go ahead and put negative 1/2 and divide this synthetically. 2, negative 1, 17, negative 9, and negative 9. And we have that remainder of 0. Now, we said that x minus 1 may be a 0, x equal to 1. So let's go ahead and place 1 into the box. And we call this a back-to-back synthetic division, and we have another 0 remainder. Now, we went from a quartic, a degree 4 polynomial, to a degree 3 polynomial. This was a degree 3. And now this is a degree 2 polynomial. So this represents 2x squared plus 18. So let's take a look at this right now. Right now, our factors, oh, they just want solutions. So they didn't ask us for factors. So our solutions are going to be negative 1/2 and whatever we can find solving this quadratic. So probably need to bring that up. Okay, and so now we can look at our solutions. After we finish this, x is equal to plus or minus 3i. So now we have 3 solutions. And we have a degree 3 polynomial. So, excuse me, we have a degree 4 polynomial. So we know that and I think I forgot negative 1/2 and 1. I think I forgot 1. That we have a degree 4 polynomial. We have 4 complex zeros. So negative 1/2, 1, 3i, and negative 3i. And those are our solutions to that degree 4 polynomial. Okay, let's take a look at number 6. Find a polynomial of lowest degree. So we do need to find a polynomial of lowest degree with these given zeros. Now 2 has a multiplicity of 2. And then we also have 3i. So let's go ahead and try to write this out. We have f of x, this polynomial. We have a leading coefficient a. And we have x minus 3i. And then we have x minus 2 multiplied by x minus 2, since that had a multiplicity of 2. But what do you notice that we didn't account for? Do we have more information? What's the information that we have? If 3i is a 0, we also have negative 3i as a 0. Okay? So now we can go ahead and I think I'll put it right after this. That's okay. X plus 3i, x minus 2, and x minus 2. Now we need to multiply these out. So I'll first multiply my complex numbers to my complex factors, and I'm going to get x squared plus 9, and then I'll multiply these x minus 2 times x minus 2. And now I will go ahead and multiply all of these terms by x squared, and then 9. And then we do have a few like terms. And I think that's it for like terms. So we have a multiplied by x to the 4th minus 4x cubed plus 10x squared minus 30x plus 36x plus 9. Okay, number 7. Find a polynomial p of x of degree 3. So they've already told us that n is equal to 3, and they're giving us zeros of negative 2i and 4. So what do we know for sure? We also have another 0 of 2i. Now this is interesting because this is going to help us solve for a. It's going to help us with that. So let's go ahead and set p of x up, and then we'll talk about that. So we have p of x is equal to a times x minus 2i, x plus 2i, and x minus 4. So now let's go ahead and simplify first. We have x squared plus 4 multiplied by x minus 4. And writing this out, we have x cubed minus 4x squared plus 4x minus 16. Now, since p of 0 is equal to 32, we can actually plug 0 in, and you can see that a is equal to negative 2. So now we can go back and write p of x is equal to negative 2 times x cubed minus 4x squared plus 4x minus 16. And let's distribute that negative 2. And there we have p of x. Okay, and we will conclude this section with something called Descartes' rule of signs, okay? So Descartes' rule of signs basically tells us how many positive real zeros we're going to have, how many negative real zeros, and these are going to be, it's going to give us the cases or the possibilities. of our zeros, okay? So the positive real zeros is the same as the number of sign changes in f of x, or less than the number of sign changes by a positive even integer. And we will just go down by 2's. And I'll show you how to do that in a table. And the negative real zeros are the number of sign changes in f of negative x. And then we will also go down by 2's. From that main number. So let's give this a try. How many sign changes do we have? We went from a positive to a negative. There's 1. A negative to a negative. Nope. I don't know why that's drawing a line there. So I went from a positive to a negative. Then I went from a negative to a positive to a negative, and a negative to a positive. So we actually had 4 sign changes. Now let's drop down by 2's, and we will have 4, 2, and 0. So we're going to look at all these cases. Now let's go ahead and find f of negative x, and we will count those sign changes. So we are just plugging negative x in, and as you can see, this is what we get. So now, counting these sign changes, we have 1, and that's it. So now we'll place 1 here, and every one of these have to be 1. Now, the number of imaginary zeros, this column must sum the total, including the multiplicities, must sum to n, and n is equal to 5. So all of these, and I better put that in a different color, all of these columns need to sum to 5 since n is equal to 5. So now we'll just fill those in. So we can say that the imaginary zeros in this case is 0, in this case is 2, and in this case is 4. And note, all of these are even numbers since imaginary zeros come in pairs. Okay, so we will find our upper and lower bounds by doing something a little bit different here. We are going to find our upper bound if all real zeros are less than or equal to b. So b is an upper bound if all of the zeros are less than or equal to. And a number a is a lower bound if all of those zeros are greater than or equal to a. So how are we going to find these boundaries? That's the definition of a boundary. We're going to go ahead and see that if c is equal to 0, and if both the remainder and the coefficients of the quotient are non-negative, then we do have an upper bound. And if c is negative, and the coefficients of the quotient and the remainder alternate in sign. And now 0, we call it a wild card. So 0 can be considered either positive or negative. Then we can say that c is a lower bound. So let's give this a try. They want us to show, so we already know, that 4 is an upper bound and negative 2 is a lower bound. So to show 4 is an upper bound, we're going to go ahead and put it in the box. And I did do that a little bit big, so I better scrunch that down a little bit. And let's go ahead and do synthetic division. Whoops. I guess we didn't have one of those missing. I don't know what I was thinking. Just retype them. Okay, so 6, negative 17, negative 12, 23, and 12. So we'll drop the 6. And then 24 minus 17 is 7. Now, what do you note? All of these are positive. All of these are positive. So if both the remainder and the coefficients of the quotient are non-negative, and none of them are, therefore, x equal to 4 is an upper bound. Okay? So now, what do we need to show now? Negative 2 is a lower bound. So let's go ahead and put negative 2 in the box. And go ahead and do your synthetic division. Now, what did you notice here? All of these alternate. Okay, so therefore, x equal to negative 2 is a lower bound. So it's kind of cool. Okay, and that concludes this section.